Can you turn your mic on?
Testing, 1, 2. I hear myself in here. Are we good? All right, can you go over to the overhead overhead camera, please? This way. Yeah, if you could pan it to the...
It isn't rotate. Yeah.
No, not rotate, just pan it this way. Yeah, way over here. I'm over here. Yeah, there we go. Thank you. All right, now that we found me. All right, sorry to keep you guys waiting. I guess my clock's a little bit slow, or it took me longer to walk over here than I thought. All right, this is E544 discussion. Hopefully that's why you're all here. My name is Aaron Freeze. I'm the TA. I have TA'd this class many times. So hopefully I'm getting good at it by now. Let me just give you my basic information. It's my name, obviously. It's my email address. Probably the best way to contact me other than office hours. And my office hours are thus. Wednesday, 2:30 to 3:30. Friday, right after this discussion, so that's going to be 2 to 3. And that's going to be in BHE 106. The number to that room will be handy for you to have if you come to see me, just in case I forget to block the door open. Other than that, this number will be useless to you, because I'm not likely to be in there at random, unless I have office hours or I'm there for something else. So if it's not during office hours, email me, and you'll get a much better response, because you can leave a message on this number, but I have no idea how to check it. So you won't really get me. You'll get nobody. A bit about me, really quick. I'm a PhD student here. I've been here for a long time. I work on photonics / device physics. And mostly what I do is simulations on the high performance computing environment here at USC. And I've TA'd a lot of courses, some of them which you might be taking as well. I've TA'd several undergrad courses, which you guys are probably not interested in. But I've also TA'd 544 several times, and I've TA'd 562A. If any of you guys are taking that or have taken that. And I've gone through the screening for actually both for SIPI and for electrophysics. So if you guys have questions about that stuff, I'm happy to answer that as well. Okay, so that's about me. Excuse me, I really have some phlegm in my throat here. One question I have administrative-wise, on DEN, I can set up some forums for you guys to ask questions. The one that has been most popular has been a student-to-student forum, so you guys can ask questions of each other. If we do set up a forum like that, it will not be monitored by Dr. Zahid or myself. It will just be there for you guys to ask questions of each other. Obviously we can go in and see it, so don't use it to cheat. But if you have I don't know what kind of questions they've even asked there before, just general stuff about the course, or looking for groups for projects, stuff like that. Would you guys want something like that, just to communicate with each other? Yeah? So student forum, yes. So I will set that up as soon as I can, probably later today. Okay, so today what I'm going to talk about is two things. I'm going to talk a little bit about the tools that we're going to use in this course, and then I'm going to do a review of transforms, which you guys have hopefully had. And so I won't do a very complete review, and it'll kind of seem haphazard, but hopefully it'll be enough to remind you guys of what you've seen before in terms of transforms and that kind of thing. So let's not skip 3. Let's skip 2. So the tools, there are, and tools is kind of a general term that I'm going to use to mean software in this course. There's ADS, there's Virtuoso, and then there's Microwave Office. All of these kind of do the same thing. Cadence. But the one that we have available to use here at the school is this one. And so that's the one that I'm going to introduce to you, the one that I'm going to show you how to use when it comes to this kind of things. And these are all circuit and RF simulators. So I will show you everything that you need to know how to do this one. So all the above simulate circuits, and they have very similar feature sets as far as I know. Obviously there's going to be differences in how they're used and that kind of thing. So if you're used to using one at work, I would encourage you to use Virtuoso so that I can actually help you with it. Otherwise you will be very much on your own, and let's say this, for this class, use Virtuoso. You'll be level with everybody else, you won't be ahead or behind, and I can actually help you, and it levels the grading field that way. So use this only, please. And to that end, I will show you everything you need to know how to do on that, in that software. Now, I'm a little bit ahead of where we are in the class as far as talking about this kind of stuff, but I just want to let you know ahead of time what I'm planning to do here. And that is starting from setting up your student account to use the software. That's what I can't see. I'm sitting up here trying to read my notes, and I'm farsighted, so everything up close is difficult for me to focus on, especially when I'm tired. And so I'm wondering why I'm getting agitated. It's my own fault. Okay, so from setting up your student account to use the software, and I will take you all the way through to simulation, plotting of results, and then after we make plots, interpretation is mostly left up to you, but it's kind of what this class is about when it gets to that stage. So that's up to you mostly. That doesn't mean that I'm going to leave you out in the cold when it comes to interpretation, but it means that if you're trying to build a matching circuit and you get a certain result at the input, you should kind of have an idea from what we've covered in the course as to what you need to do. Now, That doesn't preclude you from asking questions about anything. Some questions I just may decline to answer if I think that you should know it, or if I feel like you're using me as a crutch. But most of the time what I'll say, if it's something that I think you should know, I will send you away and say, think about it, look at it from this point of view, and then try and come back. And if you still don't have it, we'll talk about it more. Okay? Okay, so I'm going to start this stuff hopefully in 4 to 5 weeks, and it's going to seem really out of touch with what he's going through in class. So just so you know, that's coming, and it's going to be like that. The reason why I started doing it early is because a lot of times people have issues when it comes to doing the second project. They haven't set up their account, and it's this big crunch to get everything done. And so if we get that out of the way ahead of time, it goes a little smoother when that project comes around. And because that project is at the end of the semester, you guys will have other things that you have to be doing as well. And so it just makes it easier, hopefully, on you and me as well. All right, so that's enough about the tools stuff. So let's look at our transforms. So this is a radio frequency type class. So a lot of what you're going to be doing is frequency domain analysis of signals. Not exclusively, but to a large extent, it's very germane to this class. So obviously the transform of choice usually is a Fourier transform, and just because it's interesting, this guy's a French mathematician and physicist who discovered the greenhouse effect. I'm just giving my little interesting blurb about this guy, so this isn't really important. But he discovered the greenhouse effect, which I thought that was pretty interesting. As you remember for this transform, but he also discovered the greenhouse effect. But this is not very important to this class, at least material-wise. So here we go. On to our transforms. And that's the last thing I'll probably say about the greenhouse effect. Frequency analysis. And this is, like I said, just transforming, or I guess I did say I alluded to, transforming a signal from a time domain representation to a frequency domain representation. And this is done by projection onto what are called basis functions. Whoops. Now I am going to functions. Functions. And in the case of the Fourier transform, the basis functions are of the form of e, j, omega t. That kind of basis function. The reason why I mentioned that is because if you've had enough linear algebra, the basis functions are very similar to basis vectors. They serve the same purpose. It's just there's an infinite number of them, rather than one for each dimension, as there are in most linear algebra type problems. So our Fourier series, and this is for periodic signals, and it's undefined for signals that are not periodic, but definition of the time domain signal, I'm going to put a little p there to make sure, remind myself it's periodic, is the sum over the frequency domain coefficients times their basis function. So here's the coefficient n. This part here makes up the frequency, and t is just the time, the value at the time. Sometimes called the exponential Fourier series, because you can do this. You can do a similar thing for here with cosines and sines. So in this representation, little x sub n are called Fourier coefficients. Sorry, I should be making that capital F. Coefficients. And, sorry, represent the frequency content of the signal at f equals 2 pi n. 2 pi n being a multiple of the fundamental frequency of the signal. Okay. So how do we find the x of n? That's really what we're interested in here. Finding x sub n. Well, I have the time domain representation in terms of the Fourier coefficients. And so if I multiply both sides by e to the minus j 2 pi fmt, I get this. And then I can just take that inside this summation here. And I end up with 2 pi f n minus m t. And then the next step to find, or to straighten this out, this is just integrate over one period to find out what the what happens then. So I'm just going to take this guy, integrate over one period, and magic will happen. So I'm going to do it in this way, from minus t over 2 to t over 2. E to the minus j 2 pi f m t summation. And I've skipped a step here and just switched the order of the integration and the summation. So this thing only has a value, it turns out, when n is equal to m. And its value is just going to be xn. Because this whole thing will evaluate to 1. Otherwise, this term, because of the f here, which is an inverse multiple of, well, let me just write that, f equals 1 over t, right? So all of these are going to be experience an even number, well, a whole number of periods in minus t over 2 to t over 2. And so the integral of a full period of any sinusoidal function over one period, or an integral number of periods, is always 0. So I'm just writing what I just said, sorry, e to the j 2 pi f n minus m t has an integer number of periods, sorry, I'm going off again, periods in this range, minus t over 2 to t over 2. And the integral, I can take out xn because it's just a constant and this to this integration. This equals 0 for when n is not equal to m. And so the only case where it is not equal to 0 is when this integral is, or this is 0, this becomes 1, and then you have, when n equals m, you have xn minus t over 2, t over 2, dt, and that is equal to t times xn. Okay? And so what you end up finding, therefore, xn, is equal to 1 over t times the integral. Now this is just going back to this expression right up here, and substituting in the only value that gives us a non-zero result, t over 2 xp e to the minus j. Now I said n has to equal to m, so up here this n is going to become an n. M is going to become an n. Sorry. E to the j 2 pi f n t dt. And the reason why I went through that derivation is because the derivation to find the Fourier representation when it's not periodic is actually basically exactly the same. You don't have the periodic nature, but you're integrating from minus infinity to infinity, and so the same kind of thing happens, where the non-equivalent components cancel out, and you're left with an integration that looks basically like this, where instead of going from minus t over 2 to t over 2, you're going from minus infinity to infinity. This one's just a little bit easier to do, and it's just the first transform that I talked about, so I did it there. So let's do an example. Because everybody likes to see examples, right? Hopefully. So, pretty basic example. You guys have probably all seen this before. It's just going to be a box car. So, middle of this one's going to be t, and this is going to be 3t over 2 out there. And then inside here, we have the duty cycle, t naught over 2, t naught over 2. So basically what this means is that, let me specify this a little bit further here real quick. And let's make the amplitude, I'm just going to make the amplitude 1. You can make it other things. But so from t naught over 2 to minus t naught over 2 to t naught over 2, the value of the signal is 1. Otherwise it's 0. And then the frequency repeats every big T seconds. So let's find the Fourier series coefficients of this. So just going to use my form that I found up here, this one right here. And so just feeding things into that formula. I haven't specified t any more specifically than this. I have my signal xp of t, e to the minus j 2 pi f n t, integrating over t. And now I can specify this further. xp of t only has a value from t minus t naught over 2 to t naught over 2. And so that means I can limit my value, my range of integration to these ranges. Oops, I forgot one part, sorry. And I can replace, in that range, I can replace xp of t with just the value 1. So doing that, integral from minus t naught over 2 to t naught over 2, and then I'm just left with e to the j 2 pi f n t dt. Not a hard integral to do. Just take down the exponent without the t, e to the minus j 2 pi f n t, and then going from minus t over 2 to t naught over 2. And from here on, it's just substituting things in. I'll go ahead and complete it just to have the answer up here. So I have minus 1 j 2 pi fn, and then here we are, minus j 2 pi fn t naught over 2 minus e j 2 pi fn t naught over 2. Close that, close that. And then I can cancel things like the 2 here, and I realize that this is basically a sine function in here. When I take the j and the 2 out with that. So what I'm left with, 1 over t times pi n sine pardon? I thought I'd made a mistake. Not unheard of, obviously. So I'm left with this, and then hopefully you guys know that you can turn this into a sinc function fairly easily. I don't remember the exact conversion, whether you take the f or not. I don't think you do, but that's that. Hopefully that looks familiar. You guys, you've at least seen it before. You're not going to be doing, transform after transform after transform in this course. It's just good to know this. It will show up on a couple of homeworks. But the main point to take away from transforms is that you can represent a time domain signal with a Fourier domain signal. And beyond that, the most useful transforms for looking at these kinds of systems are usually going to be, for a single frequency, the transform, if that's a cosine, it's a sine, is going to be, like this. And that idea, knowing this, will get you pretty far in most cases, as long as you're comfortable with just taking a sinusoidal signal and assigning it just an impulse at f and minus f. That will actually get you through most of the transform, or most of the frequency domain analysis. when the transform homework comes up, you'll actually have to go through and do more complicated things than this, but this will get you through most of the course, and being comfortable with that idea will help you along quite a bit. Okay? So a couple more things about transforms. Average power. So this is Parseval's. The average power in a periodic signal calculate it using the time domain. Oops, minus t over 2. Time domain signal. Yes?
What's inside the bracket?
In these brackets? Oh, Parseval's? Yeah. Isn't that what this one's called? Parseval's theorem? Yeah. Caused me to panic here. I didn't write it down up here, and I was like, that's the right name, isn't it? Parseval, yeah. So it's just the magnitude squared, the integral over one period, normalized by the period. And we know that this is going to be a real signal inside the magnitude brackets. But if f of t is a real signal, then you can get rid of those brackets and just replace it with f squared of t. But the thing that people most like to do with this is what Parseval's theorem actually is, and that is to transform this into a something in the frequency domain, an expression in the frequency domain. So I'm just changing, instead of using x now, I'm using f. E to the j 2 pi f and t. Don't get confused between this f and this f. They're different. This one represents the Fourier coefficient because it's got the subscript n. This one just has an n next to it. Probably a bad choice on my part. I apologize for that. But once I run through all this, the magnitude squared of e to the j 2 pi f n t is just 1. And the integral over one period of the square of a sinusoid is it's 1, right? So essentially this part drops off. Well, actually, here's what happens. This part drops off because the magnitude squared of this is 1. So you're left with, sorry, I was trying to remember how this came about. You're left with basically this integral, which has no variable of integration, and then you have this, I mean, it doesn't have no variable integration, has no, the integration variable doesn't show up in this expression once the t goes away. So you're left with this fn squared I've done something wrong here. This bracket needs to come in here. Which you can do. When you start doing this integration over all of this summation, it has the effect of just taking out the fn components. And when you have the cross components, they cancel out because their integral over one period is going to be 0 again. So The integration drops out, and all we're left with in Parseval's final statement is this. Instead of the integration in the time domain, we have a summation in the frequency domain of the frequency domain components. Ta-da. And so, you can argue which one's easier to use. Doesn't really matter to me which one you think is easier, as long as you use one. The nice thing about this is that if you want to find, say, the power at a specific frequency, you know that it's just the magnitude squared of that that frequency component. So if you want the DC power in a signal, you just take the coefficient as that has n equal to 0 and square it. That too will come up in homework. Okay, so I'm mostly done. Did I forget to cancel that? Yeah, I can't. Yeah, you're right. It canceled with the integration. Because this integral is just going to be t, so the 1 over t and the t will cancel. Thank you. All right. So that was the Fourier series. The Fourier transform is basically the analog of that for a non-periodic signal. Transform a non-periodic time domain signal. And it doesn't have to not be periodic, because you can do a Fourier transform of periodic signals as well. You just end up with a single impulse, or well, not single impulse. You end up with values only at the what would be the Fourier coefficients. So transform a non-periodic time domain signal to frequency domain. And if I start off with the frequency domain representation this time, rather than giving you the time domain in terms of the frequency domain, I'm now integrating over all time. So that's that one, and I can come up with the next one in a similar way by doing more integration, but I don't really see a point to doing that since I already did a very similar process once, and you guys have most likely seen it before. And this is DF. And so, quick note here. A lot of times you'll see this written as e to the j omega t, and you'll have a 1 over 2 pi out front. That's just a change of variables on this thing where you substitute omega equals 2 pi f. And then d omega is now equal to 2 pi df. And so when you do this change of variables on this integration, you end up with a 1 over 2 pi out front. Pretty straightforward that. I don't know how long it took me to actually think of that myself, because I never really thought about it. I just knew that there, when you do it with 2 pi f, you have no 1 over 2 pi. When you do it with omega, you have 1 over 2 pi out front. Okay. So the last thing I want to remind you guys about for transforms, there are properties. And this will help you to take something that you know and apply to something that you maybe don't know the Fourier transform from with less steps. So I don't know a bunch of these. I have to look them up when I use them. But just to give you an example, time domain, frequency domain, frequency domain. So in time domain, multiplication of two signals like you would do for modulation. Becomes convolution. In the frequency domain. And vice versa, if you have a system that has some impulse response and you want to do the having a terrible time spelling, convolution in the time domain, it becomes multiplication in the frequency domain. And that's what gives you the whole ability to, if you have, in the frequency domain, if you have some signal and you want to apply a filter to it, let's say, this is my filter, h of f. In the time domain, I can just multiply these together and find out. So this is my signal. I call it x of f. So when I combine those, I just end up with the part of the signal that I want and nothing else, right? And all that you've done in this case is just multiply those together, whereas in the time domain, that results in a convolution, right, of the impulse response of the system with the signal itself would get you whatever the time domain representation of the signal is. Other properties, I'm not going to write these down because, well, I don't want to, but I'll just name a few. So there's time dilation, and that's basically where a signal gets spread out or shrunk in time, and that has a specific effect on the Fourier transform. Time shift results in multiplying by a phasor in time domain. Let's see, other interesting ones. I had one in mind. What was it? Oh, differentiation. So a differentiation of a time domain signal basically results in multiplying the frequency domain by j omega. One thing I do want to point out that maybe you guys haven't heard before is that all of these properties also apply to a more general set of transforms. Well, I call it more general because there's more information in it, but the Laplace transforms. And actually the Fourier transforms are a subset of Laplace transforms where you just have a zero a real component in the frequency domain, which means it's complicated, but the relationship is such that the Fourier transform is the imaginary axis of the Laplace transform. So Laplace transform. And so in some cases where you're doing, building amplifiers or that kind of thing, the Laplace transform comes in really handy because it gives you another way to look at it and define, your response that you're going to look at and to discover whether your system is going to be stable or have ringing and that kind of stuff. So with that, I'm going to wrap up Are there any questions that you guys have for me right now? Well, good, then I don't have to refuse to answer any. Not that I would. So that's it for today. Next week, I will likely talk about transistors, another review of things you've hopefully seen before. If not, that's fine. But I'll talk about structure, physics, models of them. And then I might talk a little bit about the complicated models that we use in simulation to talk about these things, just because it's kind of interesting. Okay? All right, thanks, guys. Have a good weekend.